Hi folks, welcome back to another episode of Teardown Tuesday. Today we've got something a little different. This is an induction soup warmer. And soup warmers have been around the industry forever. The basic idea is that you have a heated outer enclosure and then your soup is in a serving pot that drops down into that enclosure. And typically they have some water in there so that you get a little bit of steam and some convection currents, and that's what keeps the soup warm in the soup well. They're pretty straightforward. This particular unit works completely differently than anything else that you've ever seen as a soup well. The electromagnetic field coming out of the coil is going to interact with the iron in the bottom of the soup pot, and the iron will get warm. That electric field, that magnetic field, will begin to heat the iron. And so that pot will get hot. And you'll keep your soup warm without any water, without any wires, without any visible heating elements. And the craziest thing about it is everything inside here will be cool to the touch. There's no big coil heater or anything in here that's radiating heat. It's all done with electromagnetic energy. The upside of this, besides not having any water in it, you can see, do not add water. Induction heating is well past 90% efficient. You're almost to 100% efficiency with induction heating. And so the coil down here, once everything is warm, will just pulse on and off. But because of that high efficiency, it's really important that we monitor temperature. So I'm guessing we're going to find that these little studs are temperature probes to make sure that the actual pot doesn't get too hot, since we could potentially put a ton of heat energy into it. If we flip this over, we can see on the labeling here, it's 120 volt, 60 hertz, 800 watt. No user serviceable parts. These are the magic words. It means I really want to see what's inside it. There's a warning here about making sure that the equipment is properly grounded, and it does have a 3-prong plug. And then we've got some container sizes for the maximum amount of food that this unit can heat. So being that it's this particular model number, we can see that it uses an 11-quart inset, or soup pot. This particular model does not have any controls attached to it, and the controls would be a separate piece that would mount somewhere in the serving line, because typically this doesn't sit on the surface of the serving line. This would sit down in a countertop. It would be down below the countertop with retainer clips. So that control would plug in here on this little USB port. So now let's go ahead and open it up. Let's see what's inside it. So with just 4 screws, you've got the whole thing coming apart. And you can see there's a control board down underneath. We've got what looks like multiple probe wires. We've got a ground wire and something else here. I'm not sure what that is. But let's go ahead and see if we can get these separated. I'm going to cut the ground wire. The probe wires will just unhook. And whatever this thing is, unhook that. And then we just got to pop these 2 coil. All right. Let's start on this half. We'll go ahead and get the shield out of the way here. And you can see right away it's a pretty incredible winding of coil. So we've got just a heavy gauge copper, bare, uninsulated. And it wraps around this thermoplastic insert from the sides, from the bottom. Then it's got a piece of insulation over the ends of it where it runs back down to our control board. You can see these are temperature probes. Yeah, look like they're probably RTDs. And it looks like there's one right there in the center, that center button. But then we've also got I've also got whatever this is. I think this is probably a high limit. That's my guess. We'll come back to this because this is, I want to see what's going on there. Taking a look down at this part, you can see we've got the incoming power coming into what looks like a power supply board, and then the output from that runs through whatever this thing is, which just reinforces my belief that it's some kind of high limit safety mechanism. So if this were to open, all the power to our driver control would cut off. The driver itself, you can see it's got a couple of cooling fans, it's got some heat sinks. It looks like there's some heat control transistors here. I'm not sure what these guys are. They might be coils, because it does say caution high voltage. This particular unit has not been plugged in years, and it hasn't, I don't think it's ever been plugged in at all. So I'm not super concerned about electrical safety here. But if this were a unit that was out in the field, if it had been plugged in, used, you were trying to service it, I would take a lot of caution against sticking fingers down inside here. Looking at the board, you see there is a fuse, and then we've got some ferrite coils. This looks like maybe it's measuring amp draw. And this is probably another temperature probe for the heat sink. Interesting setup. Let's go ahead and pop this all out and let's see what's on the bottom of the board. Let's get that. Get these fans unplugged. Nice little fans. Pop this out. Now the reason for these temperature safeties is actually pretty straightforward, but it's kind of surprising. The efficiency of this is so high that if you were to just drive this continuously, you could actually start to melt metal with these coils. In fact, some of the models that are at higher voltages and higher wattage outputs can melt metal within a few minutes if the safeties don't work. So that's why there are so many thermal safeties and probes on everything. Taking a look at the board, you can see our USB input here, and then we've got probably a little control transformer and a couple relays. These guys over here, yeah, 800 volt AC, 1600 volt DC. And they've got a max temp listed. But these are the drivers for our coil. You can see their placement on the board here lines up with our connection for our coil. Interesting little setup. Let's take a look here real quick at this power supply and just see what voltage we're driving everything at. Doesn't look like it's actually a power supply. It looks like it's a noise filter. Because we're using high volt coils, the potential is there for interference to go back through the incoming power into like the panel box or other appliances nearby. So I think this is really just capturing interference. And so we've got a couple capacitors, we've got a resistor and a relay, it looks like. Going back over here to our coil base, let's pop apart this guy. Got a little thermal insulating pad. Oh wow, very, very tiny. And there's a model number. I don't see a temperature listed, but yeah, I'm pretty sure that's like a fusible link or a safety for overtemp. Then when we look at this coil assembly, it's pretty straightforward. It's kind of interesting because there's no metal here. They're just able to wrap this uninsulated. So when we talk about what principles are used in this object, it's very similar to what we see in a transformer, like a step-up or a step-down transformer, except instead of the high or the low volt side pulling in that electromagnetic energy, we're driving that into something we want to keep warm intentionally. So it's almost like a shorted transformer in that regard. We're generating an electromagnetic field, then we're capturing it with a big ferrous iron chunk that absorbs it and turns it into heat at a very high efficiency level. When we talk about how it can fail, you can see at a glance here there's a lot of places that it could fail, but there's not any one particular one that's going to always be the failure. So we've got a number of different probes that are part of the safety system. We've got that little safety link that could potentially open up if we overtempt this unit. And then we've got a number of different semiconductor components here, all of which could fail if they get too hot. So for instance, if the cooling fans here were blocked, that would probably put an end to a lot of these transistors that are controlling our high volt field. Pretty neat setup, pretty straightforward, but also something you don't get to see inside of every day. And I think these will become very popular in the future, especially as the production cost drops for the different semiconductor components. I think we'll see a lot more of these. That's it for now. Thanks for watching.
Hi folks. If you enjoyed that video, here's a few others you might like. If you want to keep up with my other projects, make sure to sign up for the email list using the link in the description. Don't forget to share, like, and subscribe to support the channel.